Okay, I'm going to just maybe skim over or gloss over, if you will, some highlights of this blog I have just posted at my blog spot over at well, if I can focus, that would help. goldenfedblogspot.com. Golden Fed, as in Golden Federal Reserve Note. And which is a little bit of a miscreation, because it's actually our credit cards that have the golden ratio embedded in them, where Federal Reserve notes have the silver ratio, but whatever. In June of 2016, I posted the Euclidean algorithm in expanded format. They cut off that last word. And that's the headpiece of my general template there on my blog area. Anyway, it's a very long piece. It's very, very long. And what I do basically is I go over the basis of the Euclidean algorithm in terms of the golden ratio. And I start with what we're familiar with, the Fibonacci number series. But as you can see, I've rearranged terms. I make two number series out of the Fibonacci and offset each with respect to the other by one position, so that the A Fibonacci series advances ahead of the B one. And N is the place value. And I start off with A equal 1, or A to the sub-0, and B sub-0 equals 0 down here, so the sub-0, N is the sub value, the term, or the term, which iteration of the cycle. So A sub n plus B sub n equals A to the n plus 1. In other words, the next A. So we don't do it. I don't do it the normal way everybody else does, like add 2 to 3 to get 5. I add 3 to 2. The 3 of A in the third position and the 2 of B at the third position to get the 5, which is the A in the fourth position. And then I carry down the A down to here to get the next B, which is what I've done here. A sub n equals B to the sub n plus 1, to the next B in the series. And I do this for a reason. It sounds more complicated, and why would I want to bother doing it this way? There's a very good reason, because the golden ratio goes beyond the mere pentagon that we are familiar with. It goes on to this septagon. And here we have 3 more golden ratios, but they come together as a set and have to be taken as their set and not mixed with other golden ratios from other sets. So here, the root 1 that satisfies this situation is A over C. So this isosceles wedge inside of a septagon, the slope of A divided by the base of C will give the first root, and then the second one will be B over A, and then the third one will be C over B, this up there. And when we take those 3 ratios and approximate them out, this is just a general, very vague approximation. 70 over 31 is pretty vague. But you keep going out to the right, it gets more and more exact, and you eventually end up with a polynomial in one unknown of x to the cubed minus 2x squared minus x plus 1 equals 0. And those are the 3 roots. And you have to make the second root. Every even root, counting downwards, you have to make negative for this to work out. And then your coefficients will end up as integers. Well, you keep going downwards like this, third order, fourth order, and it becomes pretty obvious that something is happening that's a little different than the normal Pythagorean, the normal Fibonacci series, upon which the Euclidean algorithm is based. So we're going to skip past all these other figures. I'm just skimming here. And what we do now is we want to focus back on the Fibonacci series to turn this process around. What if I wanted to find the GCD of 2 numbers, and they happen to be 2 Fibonacci numbers that are in succession of each other, namely 144 and 89. What's the greatest common divisor? Well, we know what it is. It's the number 1. But what will it look like when we unzip it? I like to call it unzipping because we're reducing the values downwards towards 0. What will it look like? Well, it'll look like the Fibonacci series in reverse. This is very unique for Fibonacci numbers. If you take the greatest common divisor of two adjacent Fibonacci numbers in the Fibonacci series, you just get the reverse of what we just did to count upwards. We get it counting downwards. And to prove that, we create a little table. Use doing my method rather than somebody else's, in which we sort these two numbers. I like to sort left to right. So 89 is smaller, so I put it in the left column. And then I lay this down, a duplicate underneath, and shift it to the right. And now I've got an empty spot, and I fill it with a 0. And now I put these two blue rows together. This one up here and this one to here, and I take the modulo. 89 modulo 0, 89, and 144 modulo 89 is 55. And then I resort them, because 89 is greater than 55. And I just keep repeating that process. And I'll get the same answer everybody else does. I just do it a little differently, a little wacky, huh? But this will stand me in good stead because we're going to move on to the cubic. Ooh, the cubic golden polynomial. We just covered this before, right? Well, here it is again. Or we skipped past it, actually. Well, if I hadn't been skipping past, this is what I would have shown you. So now let's take the greatest common divisor, or divisor, of these three numbers in the ninth position, 793, 636, and 353. And let's mix them up to start with, because then we have to sort them. Why not give ourselves extra work? And so we run a duplicate of this underneath and push it to the right, and that leaves an empty spot, and we put a 0 there. And then we stack these two blue rows, and we take subtraction now, because you know what? This is a special case of taking the greatest common divisor of numbers, in which we never have to subtract more than once. You know, normally when you do a modulo operation, you do multiple subtractions, repetitive subtractions. You get a quotient, you toss it away, and you just hold on to the remainder. Well, here we only do it once anyway, because that's what we were doing in the previous example of the golden series of numbers, the numbers we're familiar with, the Fibonacci numbers. When we take 89 from 144, we just do it once. We can't do it more than that, and we get 55. And when we take 55 from 89, we can only do it once, and we get 34. And that happens each and every time, because that's what's so peculiar about Fibonacci numbers, is we can only divide them in once, and the remainder is a prior Fibonacci number. So I figured, oh, if I can do that with the second order golden polynomial, why can't I do that with a cubic? And you know what? I might as well rewrite the algorithm and no longer take modulo. Just do subtraction. And, you know, if modulo has any kind of similarity to division such that taking modulo 0, giving you a remainder, might cause you to become squeamish, although I've seen on YouTube that nobody gets squeamish taking a modulo of a number using 0. They just carried it down because they know it's the remainder they're looking for. But this makes it even less squeamish, because now all I'm doing is subtracting. Hey, I can subtract 0 from a number, right? And then I get the original number as my remaining value. So I just take it down, and you know what? It starts to reduce and reverse itself, giving me the exact same numbers I used to build it up in the first place, until I get a single one remaining and a bunch of zeros. So this tells me how the Euclidean algorithm can be expanded by studying how the golden ratio can be expanded. And then I finish down here with a conclusion, and I give some JavaScript software, two of them, one for randomly creating numbers to find their GCD, and another one that'll simply take in any number of input values so long as they don't equal each other and they are greater than the number 0, and they're all integers. You can put in any number of integers you want to, you know, based on the limitation of your machine and JavaScript for that matter, and it'll spit out what the GCD is. In this case, it's 5, because I chose something that chose a set of 4 numbers that, of course, I knew the divisor was 5, the greatest divisor. And that concludes this overview of this page over at, if I can focus, goldenfed.blogspot.com. The Euclidean algorithm in expanded format.